Okay, so there is another testing technique as part of black box testing that is called as boundary value analysis. So where in the last lecture we talked about equivalence class equivalence class testing, right? Uh, Now today we'll talk about boundary value analysis. So the programmers often fail to properly address the special processing required by the input values that lie at the boundary of different equivalence classes, right? So in the last lecture we talked about equivalence class partitioning. There we tried to create certain equivalence classes, right? Now from each of the equivalence class you have picked one input value, right? Now here today what we try to do is, now when there are certain problems usually programmers do make while writing the program. Instead of less than, so they will write less than or equal to. That means some one value is included, let's say less than 10, less than or equal to 10. So there is a difference, right? What difference? It is the input value is differ by one value, right? So if you say instead of less than or equal to 10, if you write less than 10, that means what? So it is not going to consider 10 value, right? So it is a mistake, right? It is a mistake. So you need to test them, right? So now the what it all says, boundary value analysis, through which we try to identify these defects, right? So boundary value analysis based test suite design involves designing test cases during the values at the boundary of different equivalence classes. Okay, so you try to consider now whenever you design the test cases where you try to consider all the boundary values of these equivalence classes values, right? So we'll talk about one example, then you will be able to understand if you do not understand as of now. So to design boundary value test cases, it is required to examine equivalence classes to check if any one of the equivalence class contains a range of values. So first thing is that what you need to do, you have to check whether the boundary class that you identified, whether that contains a range of values or it has a discrete values, right? So your boundary value analysis only works for range of values. Okay, that means the boundary one equivalence class may be 1 to 10, let's say. So it's a range of values here. Okay, maybe in another some in any other example where you can see something like this, the equivalent class will have some discrete values, let's say 1, 5, 7, this sort of values, right? So in that case we cannot apply boundary value analysis. Okay, so that is what you need to understand. So for let's say for those equivalence classes that consist of discrete collection of values, no boundary test cases can be defined. That is what I said you, right? So you cannot apply boundary value analysis for the discrete collection of values. Okay. So for an equivalence class that is a range of values, the boundary values need to be included in the test suite, right? So for example, if you see here, if an equivalence class contains the range contains the integers in the range 1 to 10, okay, so it is a range of values, that means 1, 2, 3, 4, 5, 6, all of these values, then the boundary value test suite will have something like this. Okay, so your test suite will have like this. So 1 is a 0, you will have to consider why it is a 0, because it is the boundary value of 1. Okay, and you need to consider 1 also, right? As well as you need to take 10, as well as the boundary value for this is 11, but 1 to 10 within the range it is not really required, because only you need to have two boundary values, that is only the case, right? So this is the way that you will always take all boundary values. Okay, when you take these all boundary values, then probably you will be able to easily detect those less than or equal to kind of less than or equal to kind of mistakes, right? So that is what we try to say. So usually whenever you take any range values, so usually programmers when they write the conditions, sometimes they may include the boundary values, or some maybe they make mistakes like this. Okay, instead of less than, so they may make less than or equal to, or less than or equal to, instead of less than or equal to, so they make less than. So then the problem is arises, right? That can be one error. So those things can be detected by your boundary value analysis. Okay, because you see, when we are talking about the black box, only we design the test cases based on what? The input value. We have not taken into consideration the internal details, right? So internal implementations of the code that will be taken care as part of white box, right? We have already talked about. So then that means only the test suite will be designed based upon its input values. Okay, the range of input values it can be given to the function, right? So usually these are the steps one should follow when you going to design any test suite, black box test suite. So first thing is that you need to examine the input output value of the program. So what could be the possible input and output values, and identify the equivalence classes. Okay. So as I told you, so you need to find out the equivalence classes first, right? And then you create the test cases by picking one representative value from each of the equivalence class. That is what we have seen as part of your equivalence class partitioning test case design, right? And then you design the test cases considering the boundary values also, right? So this is the way that you will be going to create all design a black box test suite, right? So here is the very important step is that you need to first identify the equivalence classes. So right, so if you do not have a good practice understanding, or you do not have a good experience, probably it will be very difficult for you to find out all of the equivalence classes. So I mean, if you have a good practice, so then that means you should be able to get all of the equivalence classes. Now we'll see. So that is what about the black box testing. So boundary value analysis. Any doubts of our student? Any doubt?
No, sir.
No, sir. No, sir. Right. So white box testing, now it is also an important type of unit testing, right? A number of white box testing strategies exist. We'll talk about few of them, right? So each strategy essentially designs the test cases based on the analysis of some aspect of source code, and it's based on the some heuristics, right? So here we will, design the test cases based on the analysis of the some aspect of source code. That means we'll take into account the implementation of the code, because it is a white box, everything is transparent. Okay, here, so whatever the code that you have created for a particular module, so that will be as a input, and then we try to design the test cases, right? So here so they can be either coverage based or fault based, these two based, right? So as part of fault based testing, so usually you target to detect certain types of faults. Okay, and then accordingly you try to create the test suite, right? You're going to create the test suite targeting certain number of faults, types of faults, right? So here one example here is mutation testing. We'll talk about this, right? So how you try to detect a particular sort of faults. Okay, so here it is a mutation testing example. We'll talk about that maybe in after few slides, right? And the other one is a coverage based testing. So it all attempts to execute certain elements of the program. That means it does, you design the test cases in such a way that it is going to cover all of the statements or the elements of a program. Okay, Usually elements of a program means maybe you can think of, right, each and every branch, branches, okay, or you can think of any of the statements, particularly which comes within a particular branch condition, right? So that is what. So here, so when you have a coverage based testing, so there you try to attempt to execute certain program statements. Okay, now here are certain examples. I mean, we'll talk about all of these examples, right? One is a statement coverage, branch coverage, and path coverage. Okay, so these are the three techniques we will talk here, as well as we will talk about the mutation testing. So these are all four testing as part of white box. So testing criteria for coverage based testing, right? So here, as I told you, you have some strategy. I mean, when you apply that particular strategy, so you will be able to discover certain types of failures or the bugs, okay, or the defects. Okay, so that is what exactly the objective, right? So the set of specific program elements that is testing strategy targets to execute is called a testing criteria of the strategy. Okay, you can easily understand, right? So I mean, you try to execute certain program elements. Okay, you target that you need to execute those specific program elements so as to discover a particular type of problem. Okay, so that is what we call as testing criteria of the strategy, right? And there are some stronger testing and some weaker testing, right? What is a stronger testing strategy? So always this stronger testing strategy covers all program elements covered by the weaker testing strategy, right? If you apply weaker testing strategy, yeah, whatever the program elements that you will be able to cover, right, all can be covered by the stronger testing strategy. That is what all says, right? The stronger strategy covers at least one program element that is not covered by the weaker strategy. So that means it is a superset. Now if you're going through any stronger testing strategy, that will actually cover all of the program elements, or at least it will have at least it will cover at least one program element will be covered. Okay, uh, which is not being covered by the weaker strategy. Then only you will have a stronger strategy. Okay, otherwise they are equivalent. Okay. So now, so if a stronger testing has been performed, then weaker testing need not be carried out, right? Because you understand, right? So the stronger testing strategy actually covers at least one program element, covers one program element which is not being covered by the weaker testing strategy, right? That is what we have seen. That is, so if you have a stronger testing strategy, then need not require to apply your weaker testing strategy. But there can be this way. So let's say, for example, sometimes it will happen like this when none of two testing strategies fully covers the program elements, right? I mean, you have applied a stronger testing strategy, and you have applied a weaker testing strategy, right? And these are the two strategies you applied, and I mean, you can think of, when you apply some weaker strategy, so some of these program statements or the program elements will not be covered by whatever they will be covered, whatever are not covered by this, weaker strategy, is also not covered by the stronger testing strategy. Similarly, the program element which is not covered by the stronger testing strategy is also not covered by the weaker testing strategy. If some such things are there, then I think you require both of the strategies, because you have to cover all of them, right? So that is what the idea, right? So then the two are called complementary testing strategies. So in that case, both are required. They are complementary to each other, right? Then only you have both the testing strategies, right? You can think of, right? So when you apply both of them, you will be able to cover all of the program elements. So in that case, you can say both the testing, strategies are complementary to each other, right? So this way you can think of. Usually when you say, weaker and stronger, so this may not work in this case, but I said you, if you have two strategies and these two strategies are identifying or covering two different program statements, right, or the program elements, so then in that case you can say always, so they are complementary to each other, right? So the coverage based testing is frequently used to check the quality of testing achieved by a test suite. Okay, so you always we always apply this coverage based testing, right, to see whether whether all of the programming statements or the program elements are covered by the test suite. Okay, so it is hard to manually design a test suite to achieve a specific coverage for a non-trivial program. So what it all says is, so if you have a very non-trivial problem or a program, that means it is a very large program, it's not a easy program. In that case, if you're going to design manually the test suite, probably it will be very difficult to cover all of the program. It is very difficult to ensure that the test suite that you design will be going to cover all of the program elements in that particular non-trivial program, right? So somehow you need some sort of tools, then only you will be able to execute them. So now we'll talk about one example here through which you can talk about the statement coverage, what it is all says. So when statement coverage strategy aims to design test cases so as to execute every statement in a program at least once. Okay, so you will have to design the test case in such a way that so they should be covering all of the statements. Now here you see for this particular, this is a GCD. So how you can greatest common divisor, right? So how you can find a GCD of two different numbers, right? So you have a two numbers, then this is the pseudocode or the program for this GCD, right? Now what I say is, so here we need to create the test cases in such a way that it should cover all of the statements, right? Now let's say you take the value x and y is equal to 3. What will happen? So if x is not equal to y, what will happen? What will happen? That means it will go out of the loop, while loop. That means it will execute return x. Okay, right? So it is covering this statement, right? Now if you have a test case where x is equal to 4 and y is equal to 3, so then what is happening? So here the values are not equal. That means they are different values. That means you will be going inside the while loop, and then you check that if x is greater than or y or not. Here in this case x is greater than y because you have taken x is equal to 4 and y is equal to 3. So that means you executing this statement x is equal to x minus y. Okay, this is the statement getting executed, right? Now another test case I have taken here is x is equal to 3 and y is equal to 4. Now this thing, what, so again your while loop, in this case what will happen? So if you go with the while loop first, so you can see so they are not equal to each other. I mean they are not equal, x and y. So that means you inside the while loop. Then here x is 3 and y is equal to 4. That means the else part will be executed. That means you will be covering the statement y is equal to y minus x, right? So that means the inputs you have taken to test in such a way that it is covering all of the program statements or the program elements, right? So this is what we call as statement coverage. So you need to ensure that when you design your test cases, you should be able to cover all of the statement. Otherwise, what will happen? So the very first day when I very first topic in which we were talking about the testing, so I gave you an example there. As the else part was not going always, right? Not getting executed. As a result, you never be going to find the error which is part of the else part, right? So similarly, that is what exactly, right? So this is all called as statement coverage. Now the other one is a branch coverage. Okay, so a test suite satisfies branch coverage if it makes each branch condition in the program to assume true and false values in turn. Okay, that means, so you should have the test cases in such a way that whatever the branch, whatever the branches are, I mean, in your program, definitely you will have some branching statements, right? When you have those branching statements, so usually there will be a true part or false part, right? So you need to take the test cases in such a way that, so it should all check all the branches of that particular branching statement, right? So this is what you need to ensure, that branch coverage, right? So branch coverage, each branch in the CFG representation of the program must be taken at least once when the test suite is executed. We will talk about the what is CFG. Okay, so it is something, control flow graph. Okay, we'll talk about this, but here what it all says is, so whatever the program that you will have, we will try to come up with a control flow graph, and after that we will ensure that, so at least each of the path, linearly independent path, should be covered. That is what we will be talking about. So we'll talk about that later on. So as of now, you understand that. So you're going to cover each and every branch, right? That is what branch testing is also known as edge testing. That is also called as edge testing, right? So test suite, for the previous example, you can see, for the previous example, whatever you have seen. So here what you see, so x is equal to 3, y is equal to 3, x is equal to 4, y is equal to 3, and x is equal to 3, y is equal to 4. So these are the three test cases you have taken in the past to ensure that ensure that statement coverage. Now you will have here some other test cases now which will ensure that it is a branch coverage. Now you see x is equal to 3, y is equal to 3. We have taken in the past, here also we are taking. So by which what it is going to tell, when you take x is equal to 3 and y is equal to 3, that means this condition, what while loop condition, is true or false? It is false or true? When x is equal to 3, y is equal to 3, what will happen? What will happen in the while part?
False.
False. Okay.
False.
So x should not be equivalent to y. Okay, but here it is equivalent. That means it is false, right? So when you have false, so that means you will be directly coming to the return x. You are not going into the true part. So that means this is the test case covering the one true part. Okay, a false part. Now you should have another test case which can go through the true part. That means now you will have x is equal to 3 and y is equal to 2. X is equal to 3 and y is equal to 2. That means you are going into true part. Okay, when you going into true, that means you have covered the while branch completely. Now similarly, when x is equal to what you have taken here, 3 and 2, right? When 3 and 2, that means 3 is greater than 2. Okay, that means true part has been taken, right? Similarly, you need to have one test case we should go with the false also. That means x is equal to 4 and y is equal to 3. Okay, now you see x is equal to 4, sorry, x is equal to 3. Here you have x is equal to 3 and y is equal to 4. Now this will cover the false portion, right? If you go by this, x is equal to 3 and y is equal to 4. Now here in this case, so else part will be executed. Okay, that means both true and false has been considered, right? Now you have something, x is equal to 4 and y is equal to 3. X is equal to 4 and y is equal to 3. So here you considering x is equal to 4 and y is equal to 3. That means you are going through x is equal to 4 and y is equal to 3. That means you are going with this true condition also. You have gone through false and you have gone through true. Now you can see, right? So how many? So you have taken the condition. You see, for this if you have two cases, for while you have two cases. That means altogether you have got four cases. That means that is what? That means you have covered all the branchings. Okay, so that is what. So now your branch condition actually. So when you see now here, when you go with this sort of branch coverage, now automatically it ensures the statement coverage. Now you can check that, because in that statement coverage case we have got three case case test cases. Now those all will be covered here. Okay, automatically when you go with the branch coverage, that is why. So branch coverage is better than statement coverage, you can think of, because it is all ensuring that the statement coverage also, right? You can think of. Now there is something called path coverage also. Okay, so you have seen the statement coverage and branch coverage. Now the last one is the path coverage. Now we'll talk about this. So a test suite achieves path coverage if it executes each linearly independent paths at least once. So we will try to find some linearly independent paths, or sometimes you call them as a basis path. And when your test cases, whatever the test suite, test cases are designed, so that means so the test case should, the test should cover each and every linearly independent paths at least once. That means those linearly independent paths should be tested, okay, thoroughly. At least once you should visit each and every linearly independent paths. Okay, we'll come to that, what is that linearly independent path and all. So a linearly independent path can be defined in terms of the control flow graph of a program. It is fine, so we'll come to that, right? So what is a control flow graph? Now you can see whatever the program that we have taken, GCD program in the previous lecture, same example we are taking it right now. So what I try to do here is you assign the numbers, okay, to each and every program elements, right? So you can think of like while is 1, if is 2, and then x is equal to x minus 1, 3, 4, 5. You can give each and every statement uh, a kind of number. Okay. So now what is happening? So after giving these numbers, right, now what you try to do is you can see. So each and every number can become one vertices here, okay, in the graph, control flow graph. Now you see from 1 to you can always go to 2, okay, if the condition is true. If the condition of while the first statement is true, then you are going to the 2. That means there is a edge going from 1 to 2. Okay. Now similarly, what will happen if while loop is, if the while loop, the condition is tested, and if it is if it is false, then what will happen? Directly it will coming to which statement? It will be coming to the statement 6. Okay, that means 1 to 6 you can have always a direct edge, right? Do you understand? 1 to 6. Okay, now from 2 to, either you can go to 3 or you can go to 4. 2 to 3, 4 you can go, either you can go to 3 or you can go to 4. Now from 3 you can always go to where? From 3 you can always go to 5. Okay, you can always go to 5. Similarly from 4 also you can always go to 5, right? But from 5 again you will be going to 1. Okay, because the loop will be checked once again, right? Right, so that means from 5 to 1 you can go. That means you can always draw a control flow graph from your program code, piece of program code, right? So is it clear now? Any student, anyone here who do not understand this CFG? Or every one of you understood this?
Yes, understood.
Okay. Right. So then, so now what I'm trying to say here is, so you can always have some linearly independent paths. So now you see, now here one independent path is what? From 1 to 6. Okay. So 1 to 6 is one independent path. If you have the test cases in such a way that, while loop is, if the while loop is, false, then directly you are coming into return X. Okay. That means you are not going inside the true part. Okay. So now this means this is one linearly independent path. The other linearly independent path is something like this. Okay. 1 to 3, 3 to 5, 5 to 1, and 1 to 6. Do you understand? So this is one linearly independent path. Okay. The other linearly independent path here is 1 to 2, 2 to 4, 4 to 5, 5 to 1, and then 1 to 6. That means if you start from the statement number 1, right? So going till 6, you have three different linearly independent paths here. Okay. So do you understand now? Now, so whenever I say linearly independent path, that means, if you see, if you compare from the first linearly independent path to the second linearly independent path, if you see that, a linearly independent path will always add a new edge to the path that you identified. Okay. So that is what you say. Let's say you see 1 to 1 to 6. So this is it is a very linearly independent path. It is only one hop. Okay, here. But now you have another linearly independent path, that is 1 to 2, 2 to 3, 3 to 5, 5 to 1, and then 1 to 6. Now here what is happening? So if you see in the second linearly independent path, so there is a extra edge added, either 1 to 2 or 2 to 3, 3 to 5, or 5 to 1. So that means one new edge has been introduced in that particular path. Okay. Now if you see for the other linearly independent path like 1 to 2, 2 to 4, 4 to 5. So in this case, so the new edge here added is 2 to 4. You can think of 2 to 4 or 4 to 5. This is a new edge added. Okay. Right. So every linearly independent path will introduce a new edge in the path. Then only, so it is a linearly independent path. Okay. So a path through a program is any code and edge sequences from start node to the terminal node of the control flow graph of a program. Now you understand, right? So start node here is a 1 and the end node is the terminal node. Here is the 6. Okay. So you will always have certain number of nodes. Okay. And edges, right? So leading from the source to the destination, or source to the what you say, terminal, right? So that is what a path is. A program can have more than one terminal node, right? So sometimes you can have also two exit paths, okay, or you can have two return statements. That is also sometimes possible, right? Now test cases to cover all paths is impossible because the presence of infinite loops. Now you can see here. So in the previous CFG graph, there is an infinite loop also, right? Can you see here or not? Like you can see. So what I can do here is from 1 to 2. Okay, let's say I take the linearly independent path. This is 1 to 2, 2 to 3, 3 to 5. Sorry, I mean 3 to 5, and then 5 to 1 and 1 to 6. Let's say this is one independent path, linearly independent path, right? Now one can go by through an infinite loop also, like how 1 to 2, 2 to 3, 3 to 5, 5 to 1, again 1 to 2, 2 to 3, 3 to 5, 5 to 1, again 1 to 2, 2 to 4, 4 to 5. So there is an infinite loop also present, right? But we are not going to consider those infinite loops. Okay, if you talk about all of the input data, probably then you would not be able to, I mean, it's very difficult because there are infinite loops, so you cannot test for all of the data, right? It is not at all possible for us. So what we try to do is we try to find some linearly independent paths, right? So that means the paths which actually going to introduce a new edge, then only we will consider that path as a linearly independent. Otherwise, we will not consider that as a linearly independent path. Okay, because that linearly, if let's say if the infinite loop is introduced, so in that case, what will happen? So usually that is not going to introduce any new edge always. Okay, so as a result, so that cannot be a linearly independent path. That is what we are trying to say. Now, the path coverage testing does not try to cover all paths, but only a subset of independent paths. Okay. So what we are trying to say? So whenever you going through this path coverage, so in your, so in that case, what we try to do? So we try to cover a subset of independent paths. We try to find the independent paths, linearly independent paths, and then we apply testing to those linearly independent paths. When you apply the testing to linearly independent paths, that means you actually indirectly applying to all of the paths. That is what the idea. Otherwise, if you try to apply testing for all of the paths, that means there are infinite loops available. So that means you keep on testing for an infinite time, so which will take a lot of time. As a result, the cost will increase, so which is not at all useful, right? So linearly independent set of paths are the basis path set. So it all says it is called as linear LIS or linearly independent set. If each path in the set introduces at least one new edge that is not included in any other path in the set. Okay, so that is what I already explained you, right? So always a linearly independent set or a path. Okay, so it always introduces one new edge. Okay, and that edge is not included in any other path in the set, whatever linearly independent paths you have identified, right? So if a set of paths is linearly independent of each other, then no path in the set can be obtained through any linear operations. Okay, so that means if you have a set of paths linearly independent to each other, in that case, no path in the set can be obtained by going through this sort of linear operation like addition and subtraction. That means it should not happen like this. So by adding two linearly independent paths, you cannot create the third linearly independent path, which is available in the set of linearly independent paths. Okay, so that means this cannot be created. Okay, or by subtracting certain things, so you cannot create another linearly independent path. Because I told you, so always each and every linearly independent path introduces one new edge. Okay, so that means, so there is no way of getting some some other linearly independent path by adding one or two. Okay, linearly. So that is not at all possible. That means this is what it all says. Linearly independent set of paths are the basis paths for any path in the set. Its subpath cannot be member of the set. That is what. So that means, I mean, you can indirectly say that it is a subpath also. Its subpath cannot be part of that linearly independent set that you identified. So in that program, we have identified three linearly independent paths, right? Now, if you see that, so if you see any subpath, so that cannot be a linearly independent path. Okay, that cannot be a linearly independent path. Okay, so arbitrary path of a program can be synthesized by carrying out linear operations on the basis paths. Okay, but you can create any path. Okay, by adding these all, but they are not the linearly independent paths. Okay, it is just straightforward to identify the linearly independent paths for simple programs. For more complex program, it is not easy. So now the drawback with this is If you have a small program, maybe you will be able to easily identify the linearly independent paths. But if it is a program is very complex, it contains thousands and lakhs of lines of code, in that case, it is very difficult for us to find out the linearly independent path, because it's very difficult to draw the controversially graph of that particular source code. Okay, so this way you need to understand, right? So now there is a McCabe's cyclomatic complexity metric is an important result that lets us to compute the number of linearly independent paths for any arbitrary program. So given any arbitrary program, you can always find the number of linearly independent paths. How many number of linearly independent paths? So that is what so McCabe's has given some use some metric through which you will be able to find that. Okay, know the linearly independent paths, the number of. The McCabe psychometric complexity defines an upper bound for the number of linearly independent paths through a program. That means he always says that there is a these many number of maximum linearly independent paths are possible for that particular program. It says, okay. So what is that means it says it's a upper bound. It says that it so by McCabe's cyclometric complexity, you can get the maximum number of linearly independent paths a program can have. So it is all this is the metric, right? What it all does is so applying a graph theoretic technique to the control flow graph of a program. So whatever the program you get, that will be converted into a control flow graph that you understood now how you can draw the control flow graph of a program. And given that control flow graph G of a program, now you can always compute the cyclomatic complexity. That is the E minus n plus 2. That is equal to number of edges minus the number of vertices plus 2. So here is n is the number of nodes of the control graph or the vertices of the control graph. E is the number of edges in the control flow graph. Okay, so this will be going to tell you the number of linearly independent paths. Now you come to the program E minus V plus 2. Now you apply, you just count how many number of here vertices you edges you have. How many number of edges you have here in this graph? Can anyone tell me how many number of edges here? Seven. And how many number of vertices you have?
6.
6. 7 minus 6 plus 1, 2. How much it is? 7 minus 6 plus 2. 3. That is what I have shown you already. The 3 linearly independent paths are existing in this graph, right? So I mean, this is the graph theoretic approach through which you will be able to know that how many maximum number of linearly independent paths that can be a part of a program. Okay, clear? Is it? Is it clear? Yeah, probably you have seen this where you have seen this equation. Euler's graph. Have you heard about Euler's graph?
Yes, sir.
Yeah. So whenever you going to find that in a path, Euler's path. So this is the only equation you use, right? Number of edges minus vertices plus 2, right? So in the graph theory, so the same thing has been used here to tell you that these are the linearly independent paths, right? Now the second alternative method you have is, so according to this cyclomatic complexity on a visual basis, I mean by going through the the control flow graph, you can always count what is the linearly independent paths. So that is what it all says is, so the total number of non-overlapping bounded areas plus 1. So you have, so if you go by this graph, you have non-overlapping bounded area. How many non-overlapping bounded areas? So you have 2 non-overlapping bounded areas. One is 1, 2, 3, 5, 1. So this is the one non-overlapping bounded area. The other one is 2, 3, 5, 4. So this is also a non-overlapping bounded area. So there are two bounded areas. Okay, so these two bounded areas plus 1, that means again 3. So linearly independent paths is 3. So this way also, by going through the control flow graph, inspecting this graph, you can easily identify the number of linearly independent paths. This is the second method through which you can always calculate, okay, the total number of non-overlapping bounded areas plus 1. Okay, and if the graph is not planar, the control free structured in a programs always yields a planar graph. Okay, so but presence of go to statement easily add intersecting edges. So if you have the intersecting edges and all, so then it is quite very difficult for us to calculate, right? So for non-structured programs, this way of computing mechanical complexity does not apply. Okay, so that means for structured programs, okay, so I mean if it is a planar graph, then only you will be able to compute this way, okay, non-overlapping things. Otherwise, if it is a non-planar graph, then because you will have some intersecting edges, as a result you will not be able to find that. Okay, that would be difficult. The third method by which you can calculate is the number of decision and loop statements of a program plus 1. Okay, the other way you can calculate the cyclomatic complexity of a program is linearly independent paths is n plus 1. So n is a number of decision or loop statements. Now you can go back the program and you can see how many decision and loop statements are available here in this case. Can anyone tell me how many loop statements are there or decision statement
One loop statement.
in this program?
One loop statement, sir. While
2, sir.
Yeah, if you answer this question, then I will give you 10 out of 10 in the internals.
Sir, 2.
How many loop statements or branching statements?
one loop statement, sir. One loop, one condition. Total 2.
Hello, is he here? Someone?
Hello.
Oh, yeah. Actually, my mic was muted somehow. I do not know how it has happened. Right. So that's the reason. Okay. Can you tell me how many number of conditional statements or the loop statements you have here?
One loop statement, one condition.
Okay. There are two control structures. That means two plus 1. So here also, this way also you can identify that the number of linearly independent paths, right? So these are the three ways that you can always get the linearly independent paths, and then you design the test cases in such a way that you will be covering each and every linearly independent paths. That is what we say path coverage, right? So as of now, we'll stop here today. So maybe in the tomorrow exam, so till this topic, that will be there in the exam, right? And also video. Okay, I stop the recording. So any doubt so far?